Hi everyone, welcome to the second week of ITD 151. Today I'll be covering the lecture 3, which is on data storage. We can skip slide 2 to slide 4 because this has not been covered yet. We will do this subsequently. So what we will cover today includes DBMS, Database Management System, Relational Data Model, as well as Structural Query Language SQL. In particular, we'll be doing a lab exercise on SQL, which require a submission to Polymore. So next, I have a video clip on a database, which you can access and view it during your own free time. So first of all, what is a file-based system? So a file-based system is a collection of application programs that perform services for the end users, such as production of reports. So each program is actually different, and they define and they manage their own data. So some of the characteristics which file-based system has is that it focuses on data processing needs of individuals, and it focuses on specific applications, each with its own set of a data file. And what happens is that the program data dependence, in the sense that the file-based system is highly dependent on the data that is being stored locally in the system itself. The next slide will provide an example of what this means. So down here we see two file-based systems. One is for sales, one is for contracts. But what we realize is that they both require data entry and reports, file handling routines, file definitions. But yet each of them is being stored in their own individual file-based systems. Hence there is a duplication of both property, client details in the sales and contract departments. So what are some of the key limitations of file-based systems? These include the fact that each of them owns their own set of data. Each program owns their own set of data. So it's actually quite difficult to process them. There is a duplication of data, as we see in the previous slide. Despite the two systems requiring the same data, and yet you have the same data held by the different programs. So there's a wastage of storage space, and there's a loss of data integrity. And why is that so? So assuming in the previous slide, some changes are made in the sales file-based system. The change will not be reflected in the contracts file-based system. So this affects the integrity of the data. When the sales team and the contracts teams actually looks at the assumingly same set of data, but some changes has already been made to them. Data dependence, as what I described earlier. The program, the data is being stored within the program itself. So any file structure is defined in the program code. If you want to change it from a remote centralized place, that is not possible. So next, which is why to solve these problems, there's a need to come up with a database approach where data is being stored separately and independently, and the data can then be shared with the different programs. So the definition of the data is embedded in the applications programs, rather than being stored separately and independently. So this is more effective, alright. So a new approach where we have a database and we have a database management system. So in this database environment, description of the data is stored separately and independently in the database. The database can then be shared by many application programs. So accessing to the database by these programs are through the database management system, DBMS in short. So this is how a database approach would work. Again, here we have the sales application program and the contracts application program. So what they then do is that they have, the different applications programs will access the database through the DBMS, okay, which serves as an interface. So each set of departmental applications programs handles data entry, data maintenance, and the generation of reports. However, compared with the file-based approach shown earlier, the physical structure and storage of the data are now managed by the DBMS. So you can see that the data is no longer duplicated in each department. There is only one set of common data shared by both departments, and this is found in the database. So to summarize, alright, this is the characteristics of a database. Okay, it's a shared collection of logically related data and a description of this data designed to meet the information needs of an organization. So later on in the lab exercise, you have hands-on, okay, and you will visualize, you will be able to experience for yourself how this works. So the catalog is a place where, among other things, all the various schema, okay, and all the corresponding mappings are being kept. So there's something which we call the meta data, alright, okay, found in the system catalog. It provides the description of the data, okay, to enable the data independence. So the database is a single large repository of data that can be used simultaneously by many departments and users. The database not only hosts the organization's operational data, but also a description of this data. So whoever accesses the data will know what each and every of the attribute actually means. So DBMS, so as shared earlier, the DBMS is a software system, alright, that interacts with the user's application programs and the database. And typically, a database provides the following facilities. It allows the users to specify the data types and structures on the data to be stored in the database. It allows the users to insert, update, delete, and retrieve data from the database through a data manipulation language. So it also provides access control. Okay, so typically access is granted on a needs basis. You access it only when you need it. So next we have a difference between a text file and a database file. So on top we have what we call a text file, which is used in a file-based system, and only the data is stored. But by looking at the text file alone, we might not fully appreciate what the text file is trying to tell us. And this is in contrast to a database file, which stores both the metadata and the data itself. So on the left hand side, we have the metadata, which tells us which are the file fields, and then what are the types. So for example, employee number is of the type number, and name is of the type text, gender is of the type text. So in the data itself, you see employee number, name, gender, birth date, salary, and the salary grades. So everything is well defined in a database file compared to a text file, which is found in a file-based system. So the three-level architecture of a DBMS comprises of an external, a conceptual, and an internal level as depicted in the above figure. So the external level is the views that users get to see. Alright, it's the interface to the users. The conceptual level is the community view of the database. This conceptual level describes what data is stored in the database and the relationships among the data. And we have the internal level, which is the physical representation of the database on the computer, and this level describes how the data is stored in the database. So at each level, we have a schema to describe the data in that level. So the three schemas are only descriptions of the data. The data that exists in this whole setup is found at the physical level, okay, right at the bottom, at the database level. That is where the data are being stored. So next, we also have the three levels of architectures of DBMS. So I have earlier shared, what these levels actually mean and what do they do, the functions of each of them. And here is a illustration of a database schema in three levels of the architecture. So down here we have two different views of staff details, and they are then combined, okay, view 1 and view 2, and they are then merged into one single conceptual view. And in this merging process, the major difference is that the each view has been changed to a date of birth view, DOB. So the DBMS maintains the external and conceptual mapping. Example, it maps the staff number, okay, or S number view of the first external view to the staff number view of the conceptual record. So view 1 we have S number, view 2 we have staff number, but they actually refers to the same thing. So the conceptual level is then mapped to the internal level, which contains a physical description of the structure of the conceptual record. So at this level, we see a definition of the structure in a high-level language. The structure contains a pointer and next, which allows these staff records to be physically linked to form a chain. Note that the order of the fields at the internal level is different from that of the conceptual level. So again, the DBMS is the one that maintains the conceptual and the internal mapping, and this is not visible to the to the users at the external level. Next, okay, why do we want to have these three-level architectures? The key purpose is to provide the data independence, alright, which means that the upper levels are unaffected by what happens at the lower levels. Okay, so for example, I make a change to the database, the physical layer, the viewers can continue to access the data. So for example, when there's a new information of staff, say the handphone number is added to the conceptual level, alright, it will not affect the existing external view, view 1 and view 2. So what this means is that the program users, okay, at the two external views are not affected even as I make changes to the data at the lower levels. Okay, next I have some review questions. A set of programs supporting the creation, maintenance, and operations of a database, okay, is called a DBMS, okay, a database management system. So a database schema, second one, a database schema is a description of the database using a specific data model. And the third question, which one of the following is not a level of the three-level architecture of DBMS? The answer should be D, application. Okay, so internal, external, conceptuals, they are part of the three-level architecture of DBMS. Next, let's talk about relational model terminology. So what is a relational data model? Alright, a relational data model is based on the mathematical concept of a relation. Okay, it organizes and represents data in the form of a table. Okay, so in fact, okay, a relation is basically a table with rows and a column. So a tuple is the row of a relation. Okay, a tuple is a row of a table. Attribute is the column of the table of the relation. So a domain is a set of allowable values for each attribute. So looking at this example of a relation, example of a employee table. So down here the rows are we call them tuples, and we have the attributes which are the columns. So in terms of tuples, alright, we have employee ID, and then we see all the tuples contains all the employee numbers. Alright, and the domain is a string of 9 characters. For name, attribute name, the tuples comprises of strings of 30 characters. And attribute, okay, gender, okay, the tuples comprise of a character M or F. Okay, so in alternative terminology of the relational model terms, okay, so there are a few things we can see here. Alright, the formal term, okay, a relation, is actually what we call a table, okay, or a file. A tuple is a row or a record, and attribute is a column or a field. So the properties of relations. So to illustrate the meaning of the above properties, referring to the employee relation in the earlier slide. So the name of the relation is employee, and it should be unique within a relational database. Since each cell should contain only one value, it is illegal to store 2 phone numbers, okay, in a single cell, or to store 2 employee numbers in a single cell. And there should be no duplicate tuples in the employee relation. We can exchange columns and rows, alright, but the data stored will still be the same. And in terms of relational keys, okay, I'd like to introduce a few concepts here. What are the different types of relational keys? Okay, first thing is a candidate key. So a candidate key is basically something that can uniquely identify each tuple in a relation. So referring to the example on the right hand side, there are possible candidate keys would include admin number and the NRIC number. Okay, primary key is a candidate key that can be used to identify the tuples, for example, admin number. Alternate key is basically a candidate key that is not selected to be a primary key. So for example, if we had selected the admin number to be the primary key, then the NRIC would be the alternate key. And on top of that, we have a foreign key attribute which provides a logical link between the tables. And we have more examples to illustrate that. But before that, let's look at what are some of the criteria of choosing a primary key. So it must be able to uniquely identify the tuple. Okay, so minimum set of attributes. Okay, it must be the least likely to have its values changed, least likely to lose its uniqueness, fewest characters, and easy to use from the user's point of view. So here we have a relation, okay, with the name department. So the exercise here is to identify the candidate key, the primary key, and the alternate key in the following table. So down here, the candidate keys would be D number and D name, since both are unique identifiers. So the primary key, we can choose it to be the D number, and in that case the alternate key would be the D name. So a foreign key example. So a foreign key, okay, is a attribute, okay, with run relations that matches the candidate key of some relation. So in this case, looking at the tables on the left and the right, so the foreign key in the student table on the left is the school code. Okay, so the school code, which is the foreign key in the student table, is then linked to the primary code, okay, primary key in the school table. Okay, so this is how we work. So the question here, is there any foreign key in the school table? Okay, so this is a question which you can think through. So what are some of the integrity rules for relational databases? So first thing, they must be able to be specified on a relational database schema, which we will learn more through a hands-on exercise. So the purpose is to ensure accuracy and integrity of the data in the database. So two key principles, okay, so the primary key in the base relations must not contain any null. Alright, the primary key must not contain any null. And if the foreign key exists in the relation, the foreign key must match a candidate key value of some tuple in its home relation, or the foreign key value must be wholly null. And we have some examples to illustrate what this means. This is an example of a violation. Okay. In this example, student number is a foreign key in the project relation. So according to the referential integrity rule, all values in the student number must exist in student number in the student relation, or it has to be now. However, in this case, the value, student number 879 is not found in the student relation. It violates the referential integrity rule, and the update or insert operation of this tuple will fail. So what happens on the attempt to delete the target of a foreign key reference? So referring to the previous slide, what happens if the user attempts to delete student number 121, which was referenced by project number 1? So 121 is referenced by project number 1. So we can have a few possibilities. Either we do not allow that to happen, by restricting it, or we can do a cascading. So if the reference tuple is deleted, delete the related project as well. So if student 121 is deleted, we delete the related project 1 as well. We can also nullify it in the sense that we can set the student number to null if the reference row is deleted. Some review questions. The constraints that apply to data items to make sure that the data is valid and consistent, is called integrity rules. Second one, identify the primary keys and foreign keys in the following relational schema. So for the student table, the primary key will be student number, and for the student module table, the primary key will be module number, and we can have a foreign key, which is the student number, which is related to the primary key in the student table. Next, we'll go to the structural query language. Structural query language (SQL) has emerged from the development of the relational model. Over the past few years, it has evolved to be a standard for relational database language. So what is a SQL? It's a comprehensive database language. It allows the users to create the database, perform insertion, modifications or deletions. It also allows queries to be performed. So there are two major components of SQL. One is the data manipulation language for manipulating the data. The other one is the data definition language for defining and creating the database and the table structures. Some of the key command that we are going to use. First thing is the select statement. So this is the most important in the SQL statement. It's what we use to retrieve and display data from one or more table. So besides retrieving the details or individual records using this statement, you'll also be able to use select statement to group and summarize the data. So if you notice, the select statement typically occurs at the top of your syntax, followed by from. So you need to select a distinct column list or distinct attribute, followed by from the table name. So the order of the clauses cannot be changed, and you should take note of it. So down here you have another example. To retrieve information, the syntax here is select the column list and then from the table list. So in this case, we can have a syntax, alright, to select zip code, file name, and the I name from the customer. Okay, so you can use select command, okay, to select these three attributes from the table. And this is the end outcome that we will get. Okay, zip code, okay, first name and last name. To retrieve distinct column values, okay, and what it means is to eliminate the duplicates. So for example, okay, down here we have a zip code and you see that there is duplicated zip code. We can also use SQL to select only the distinct zip codes. Okay, so how do we okay, we can also have calculated columns by performing arithmetic operations. So for example, we select the product number, the unit price multiplied by 1.1. What it means is that we want the price to increase by 10%. Okay, we can select the unit price and we multiply it by 1.1 to give us the new unit price. And here, okay, this is what we have. Alright, okay, so we have the new unit price from the products over here, and then the example below. Okay, we can select the shipping date. Okay, we can select the order date. Alright, and we can compute the span, which is basically the number of days taken for shipment. Alright, so we can also add conditions. Okay, we can select certain rows based on the certain conditions. So to restrict the rows to be retrieved, okay, we can set certain conditions. So in this case, we can select the product numbers with the unit price from product where the unit price is more than 500. So in this case, you'll notice that only the product number 113, okay, gets selected, okay, because its unit price is more than 500. Okay, row selections using the where clause. Similarly, we select the order number, the shipment date minus the order date, okay, from orders, and we can select where the span, okay, is more than shipment, more than 14 days, meaning ship date minus order date more than 14. Okay, so in this case, you see that only order number 1005 is being selected, as the span is 16, which is more than 14 days, more than the 14 days, which is the criteria that is being set. We can also select a range of values. Okay, so for example, we can select where the salary is more than 5,000. We can also select where the state code is equals to the CA, California. Alright, we can also select a range, okay, between 5,000 and 10,000, or where the order date occurs between 1st July to 31st July. So we can also use set membership, okay, where the position is in managers or deputy managers. Alright, for example, we only what this example means is that we will only select the managers and the deputy managers. So we can also do a pattern match. So for example, we can use the term address like AMOQ, okay, or where the state code like A, okay, so that we retrieve string values with AMOQ or with the state code A. Okay, so these are some of the codes. Alright. Syntax. Alright, column list, column name, column numbers. We can also have codes to arrange them in descending order. Okay. So here are further examples. Okay, to sort in descending order of the zip code. Okay, since select stars. Alright, from customer, order by the zip code descending, meaning that you select all the data from the customer table and you order them according to the zip code in descending order. Next one, to sort in ascending order of the last name. So you select zip code, last name and the first name from the customer table and you order by 2, which is the last name. So by default SQL, okay, will sort them in ascending order. So you don't have to, if you want to sort them in ascending order, you don't have to state that it has been ascending, is going to be in ascending order. It's only when you want to sort them in descending order that is where you have to tell the SQL. Okay. And the next one, sort in ascending order of a supply code followed by descending order of a unit price. So select all the data from product, order them by supply code followed by the unit price in descending order. So here are some basic select statement. Okay, select the attribute from the table name. Okay, inner join. Alright, in the exercise today, in the lab exercise, you will see how we do inner join. Alright, and then you can lay down certain conditions using where, and you can order them based on certain criteria. Okay, oops. Okay, so to do a multiple table queries, so to obtain information from different tables, example the customer table and the order table. Okay, so the data that you want, the information that you want could be stored in 2 or more tables. For example, you want to display the customer name and all the orders he has made. So the customer info is found in the customer table, while the order info is found in the order table. So in this case, you could use a inner join, okay, to select, so whereby you select the first name from the customer table and then you inner join it with the orders table, so you join the 2 tables. Alright, and the condition to join them is such that the customer numbers in the first table, customer table, must match with the customer number in the orders table. So down here we have a few examples. Okay, first thing, when we join table, we need to identify the matching columns for the two tables. So in this case, the customer and the order tables have a one-to-many relationship. Each customer can have a few orders. Alright, so the customer number in the order table becomes the foreign keys whose values must come from the primary key of the customer table. So in this case, the foreign key and the orders table, the foreign key is the customer number, and it links to the primary key in the customer table. So this is an example of a inner join, okay, where we join them according to the customer numbers. Alright, so this is an example of the how we do inner join. First thing, we must include the table from. Okay, so include the inner join conditions. Okay, so they must have compatible data types. Okay, so in this case, as the customer number is where they have in common, so we can use that to join the two tables. So some review questions here. To write the following select statements. Okay, list out the department name where Jack is a manager. Alright, so for this, the statement will be select the name from department where MGR manager is equals to Jack. Okay, I say again, to write this select statement, it will be select the name. Okay, select the name from the department, okay, where MGR is equals to Jack. Next one, the select statement to order the department information by date of manager start date. Select star, okay, which means select all the data from department table, order by MGR start date. Okay, I say again, for the second one, we will write select star from department, order by MGR start date. Okay, that's all I have for this lecture.